Our flares are explosive bursts of energy that occur on the surface of the Sun, releasing vast amounts of radiation into space. These phenomena are categorized based on their intensity, with X-class flares being the most powerful. Understanding solar flares is crucial, as they can significantly impact both our planet and the technology we rely on daily. When an X-class solar flare erupts, it can unleash energy equivalent to millions of hydrogen bombs. This intense release of energy can disrupt the Earth's magnetosphere, leading to a variety of effects. One of the most immediate impacts is on radio communications. High-frequency radio waves can be absorbed or reflected by the ionosphere, which is affected by solar activity. As a result, pilots, sailors, and emergency services that depend on radio communications may experience interruptions or complete blackouts during these solar events. But the effects of X-class flares extend beyond just radio disruptions. They can also induce geomagnetic storms that affect power grids, satellite operations, and GPS systems. For instance, satellites may experience increased drag or even damage to their electronic components, while power companies must take precautions to prevent surges that could lead to outages. So why should we care about solar activity in our daily lives? The truth is, solar flares can influence everything from our communication systems to our navigation tools. As we become increasingly reliant on technology, understanding these cosmic events becomes essential. By staying informed about solar activity, we can better prepare for potential disruptions and appreciate the intricate relationship between our planet and the Sun. In this video, we'll delve deeper into the fascinating world of solar flares, focusing on the powerful X-class flares and their far-reaching effects on our technology and daily lives. Understanding solar flares. Solar flares are sudden and intense bursts of radiation that occur on the Sun's surface, resulting from the release of magnetic energy stored in the Sun's atmosphere. These explosive events can vary significantly in intensity and are categorized into different classes based on their strength. The classification system includes A-class, B-class, C-class, M-class, and the most powerful X-class flares. Each category represents a 10-fold increase in energy output, with X-class flares being the most potent and capable of causing significant disruptions on Earth. The science behind solar flares is rooted in the Sun's magnetic field. The Sun is a massive ball of plasma, and its magnetic field is constantly shifting and evolving. When magnetic field lines become tangled or twisted, they can suddenly snap and reconnect, releasing enormous amounts of energy in the form of light and radiation. This process is often associated with sunspots, which are cooler, darker areas on the Sun's surface that indicate intense magnetic activity. When a solar flare occurs, it can have profound effects on Earth's atmosphere. The radiation emitted can travel through space and reach our planet in just a few minutes. Upon arrival, this energy interacts with the Earth's magnetosphere, leading to phenomena such as auroras, which are beautiful displays of light in the polar regions. However, the impact of solar flares is not limited to visual spectacles. They can also disrupt radio communications, navigation systems, and even power grids. Understanding solar flares is essential, especially as we become more dependent on technology that can be affected by these cosmic events. By studying solar activity, scientists can better predict when flares might occur and help mitigate their potential impacts on our daily lives. In the next section, we will explore the specific effects of X-class solar flares and their implications for our technology and infrastructure. The X-class solar flare. Recently, the Sun unleashed a powerful X-class solar flare, a classification that signifies its extreme intensity and potential for disruption. To be categorized as an X-class flare, the event must produce a peak brightness of at least 10 to the -4th power watts per square meter in the X-ray spectrum. These flares are known for their ability to release massive amounts of energy, often resulting in significant impacts on Earth's atmosphere and technology. The recent X-class flare occurred on insert-specific date, reaching its peak intensity at approximately insert-specific time. This particular flare was classified as an X2.5, indicating that it was more than twice as powerful as the baseline for X-class flares. Such intensity can lead to heightened geomagnetic activity, which can disrupt radio communications and navigation systems, as well as create stunning auroras visible at lower latitudes than usual. Space agencies around the world closely monitor solar activity, and this flare was no exception. NASA's Solar Dynamics Observatory, SDO, captured stunning images of the flare as it erupted from a sunspot region known for its magnetic complexity. Observations indicated that the flare was accompanied by a coronal mass ejection, CME, which is a significant release of plasma and magnetic field from the sun's corona. This CME was projected to reach Earth within a few days, raising concerns about potential geomagnetic storms. Notable data from the flare included increased levels of radiation in the upper atmosphere, which were detected by various satellites. These observations are crucial for understanding the flare's impact on Earth and for predicting the effects of future solar activity. As we continue to study these powerful solar events, we gain valuable insights into the sun's behavior and its influence on our planet, emphasizing the importance of monitoring solar flares for both scientific and practical reasons. Impact on radio communications. The recent X-class solar flare had a significant impact on radio communications, triggering widespread blackouts across the Pacific Ocean. These disruptions are primarily caused by the interaction between the flare's intense radiation and the Earth's ionosphere, a layer of the atmosphere that plays a crucial role in radio wave propagation. When a solar flare occurs, it releases a burst of X-rays and extreme ultraviolet radiation, which ionizes the particles in the ionosphere. This sudden increase in ionization can absorb or scatter high-frequency radio signals, leading to temporary blackouts. The regions most affected by these radio disruptions included parts of the Pacific Ocean, particularly affecting areas such as Hawaii and the west coast of the United States. Mariners, aviators, and emergency services operating in these regions experienced significant communication challenges. The blackout was particularly pronounced during the peak of the flare, with reports indicating that high-frequency HF radio communications were severely degraded or completely lost for several hours. Several communication systems were impacted by the flare, including aviation communication networks that rely on HF radio for long-distance communication. Pilots flying over the Pacific often depend on these frequencies to stay in contact with air traffic control and other aircraft. Additionally, maritime communication systems faced interruptions, affecting ships navigating through the region. Emergency services that utilize radio frequencies for coordination and response also experienced disruptions, raising concerns about safety and operational efficiency. The effects of this solar flare serve as a reminder of the vulnerability of our communication systems to solar activity. As we continue to rely on technology for navigation and communication, understanding the mechanisms behind solar-induced radio blackouts becomes increasingly important. Monitoring solar activity and preparing for potential disruptions can help mitigate the impacts of future solar flares on our daily lives and critical communication infrastructures. Global reactions and preparedness. As solar flares become increasingly recognized for their potential to disrupt technology and communication systems, governments and organizations around the world have established protocols to monitor solar activity and respond effectively. Space weather monitoring is a collaborative effort involving various agencies, including NASA, the National Oceanic and Atmospheric Administration, NOAA, and the European Space Agency, ESA. These organizations utilize a network of satellites and ground-based observatories to track solar activity, providing real-time data on solar flares, coronal mass ejections, and other phenomena that could impact Earth. Preparedness for technological disruptions caused by solar flares is crucial, especially as our reliance on technology continues to grow. Organizations in sectors such as aviation, maritime, and telecommunications have developed contingency plans to mitigate the effects of solar activity. For instance, airlines may reroute flights or adjust altitudes to avoid areas experiencing radio blackouts, while power companies implement measures to protect their infrastructure from geomagnetic storms. By anticipating potential disruptions, these sectors can maintain safety and operational efficiency during solar events. In response to significant solar activity, space weather agencies often issue advisories and alerts to inform the public and relevant industries. These advisories may include warnings about expected radio blackouts, potential impacts on GPS accuracy, and the likelihood of geomagnetic storms. For example, during the recent X-class solar flare, NOAA's Space Weather Prediction Center issued alerts that detailed the expected effects on radio communications and navigation systems, allowing organizations to take proactive measures. The global response to solar flares highlights the importance of collaboration and preparedness in the face of natural phenomena. By monitoring solar activity and issuing timely advisories, governments and organizations can better protect critical infrastructure and ensure the safety of individuals who rely on technology for communication and navigation. As we continue to advance technologically, staying informed about solar activity will be essential for minimizing disruptions and enhancing resilience against solar-induced challenges. Conclusion. In this video, we explored the fascinating and impactful world of solar flares, focusing specifically on the recent X-class solar flare that captured the attention of scientists and the public alike. We discussed how solar flares are categorized based on their intensity, with X-class flares being the most powerful and capable of causing significant disruptions to our technology and communication systems. The recent flare not only demonstrated the sun's immense energy, but also highlighted the potential for radio blackouts across vast regions, particularly affecting areas over the Pacific Ocean. We delved into the mechanisms behind these disruptions, explaining how the intense radiation from solar flares interacts with the Earth's ionosphere, leading to temporary communication challenges for aviators, mariners, and emergency services. The importance of preparedness for such technological disruptions was emphasized, showcasing how governments and organizations monitor solar activity and issue advisories to mitigate the impacts of solar events. Staying informed about solar activity is crucial in our increasingly technology-dependent world. Understanding the implications of solar flares allows us to better prepare for potential disruptions and appreciate the intricate relationship between our planet and the sun.